I welcome you all in this course on power plant engineering. Today we will discuss about the instrumentation in power plant. Instrumentation in a power plant, I mean it is an integral part of a power plant, because without instrumentation power plant cannot work at all, because we need parameters. These parameters, they do control the performance of the power plant, and for the safety purpose also we need instrumentation in a power plant. So today's topic to be covered are general aspects of instrumentation first of all, then type of instrumentations which are used in power plants, and mainly will be discuss pressure measurement, temperature measurement and the flow measurement. Now we will start with the general aspects of the instrumentation. So general aspects. First of all, if we have instrumentation, we can provide operating guidelines. To an operator, because the pressure should vary in this range, current should vary in this range, or humidity should vary in this range, or exhaust gas analysis, CO2 should remain in this range, or oxygen should remain in this range. So this operating guidelines can be provided to the operator if the plant is properly instrumentated. Then is performance. To judge the performance, we need the values about the performance parameters. So for that purpose also the instrumentation is required. Then maintenance. For the maintenance of the power plant, or repair guidelines have to be provided to the worker. So for the maintenance and repair also we need instrumentation in power plant. So there are several reasons. Economical operation of the power plant, we need instrumentation. Right, cost allocation also we need instrumentation. So instrumentation is an integral part of the power plant. So without instrumentation, power plant cannot work. And major, suppose you go for a thermal power plant, the major thing is pressure and temperature. Right. So there are two things. One is gauge pressure. Now second is vacuum. Now gauge pressure is, suppose this is zero pressure, no pressure at all, this is datum line, zero pressure, and this is your atmospheric pressure, and the gauge pressure is the pressure above atmospheric pressure. This is gauge pressure, right. So at atmospheric pressure the gauge pressure is 0. When the gauge pressure is, suppose atmospheric pressure is 1 bar and gauge is showing 0.5 bar. So the absolute pressure is 1.5 bar. Right. Now third thing is vacuum. When we talk about the vacuum, first we should know what is ideal atmospheric pressure. Ideal atmospheric pressure is at 100 meter from mean sea level. Mean sea level is known as the datum of equal or line of equal energy, mean sea level. So at the mean sea level, 100 meters from the mean sea level, right, the atmospheric pressure is, at the mean sea level, the atmospheric pressure is the ideal atmospheric pressure, one atmospheric pressure. So one atmospheric pressure is 101, 325 kilopascal. 1 Pascal is 1 Newton per meter square, right. So this is the atmospheric pressure, this is in SI unit. But if you go to the power plant, you will rarely find gauges and indicators in SI unit. Mostly either they are in SI units or in MKS unit, or mix of SI and MKS are also there. Kilopascal or kilopascal per meter square is the kilopascal is the unit which is used in SI system. MKS system, it is kg force per centimeter square. In MKS, it is, we can always find 0.0 325 divided by 9.81. It will come around 1.03 something into this is kilopascal into 10 to power 4 kilogram force per meter square, and it comes around because it is here it is kilopascal, 0.10325 will be multiplied by 10 to power 3. So, it will come around 1.03 kilogram force per centimeter square, because meter square is converted. So, this is convenient to remember, right. Now, pounds per square inch, there is also a unit in SI unit. Many of the pressure gauges in old power plants you will find in pounds per square inch. So, 1 pounds per square inch is equal to 14.696 pounds per square inch is 1 atmosphere. 1 atmospheric pressure is equal to 14.696 psi. So, if this is a multiplying factor. So, whatever pressure is there in terms of atmospheric pressure 101.325 kilopascal, and you just multiply this with this one, you will get the pressure in pounds per square inch. There is a pressure 1 atm. Nowadays it is not in use. 1 atm. 1 atm is 1 kg per centimeter square. It is not being used nowadays. And vacuum normally is expressed in terms of torr. Torr is pressure equivalent to 1 mm of Hg mercury. So, 1 mm of mercury 10 to power minus 3 into rho into 9.81. So, it comes around 133.3 Pascal. That is 1 torr pressure. So, this is normally vacuum is expressed in terms of this torr. Now, there are several instruments which are used for the pressure measurement, and the simplest and the most reliable instrument is manometer. Right? Suppose in a pipe, water is flowing in a pipe, you fix a tube here. Pressure in the pipe is, let us say, 2 atmospheric pressure. Outside is 1 atmospheric, right? So, you will get it is high, 2 atmospheric, suppose 1.2 atmospheric pressure. So, outside column you will find equivalent to 0.2 atmospheric pressure. Normally for this column is P is equal to rho GH. Rho is the density of the fluid, G is the gravity, and H is the height. So, this height is directly proportional to the pressure. So, you can always make a scale on this and can find out what is the pressure, absolute pressure, or inside this tube. There are U-tube manometers also. They are very popular in pressure measurement. Normally, they are also used for the differential pressure measurement also. And the principle is very simple. It is filled with it can be a single fluid or it can be a multiple fluid depending upon the requirement. And when it is connected to the 2 pipes, suppose this is one pipe, this is another pipe, right. So, if they have certain pressure difference, so pressure difference can also be measured with the help of U-tube manometer. So, this is for example P1, this is P2. So, P1 minus P2 is going to be equal to rho GH. This is the height, because the pressure is high here. So, fluid will lift in this limb because it has 2 limbs or 2 arms. So, if the pressure here is high, this level will be lower than this level. So, this difference in H will give the difference between pressure between these 2 pipes. So, it is expressed in dry. So, here also we can easily find or for absolute pressure, of course, this side is suppose exposed to atmosphere, this side is exposed to atmosphere. In that case also you can make the pressure. So, this is very reliable, and even it is used for the calibration also for the pressure gauges. You can always calibrate the pressure gauges using U-tube manometers. Their output is quite reliable. Then diaphragm type of, because normally in plants U-tube manometers are not used because their dynamic response is very poor. right? And it's the glass tube, it is fragile also. Nowadays, pressure gauges are available, dial type of pressure gauges are available. In dial type of pressure gauges, there is a tube which is known as Bourdon tube. Now, the beauty of the Bourdon tube is, if you feel it is a tube of elliptical cross section, if you pressurize the fluid inside the tube, it will expand, but the change in the diameter will be negligible in comparison to the expansion in the tube, right. So, what happens in a dial type pressure gauge, the another end of the Bourdon tube is fixed here. So, when the tube is pressurized, there is a movement here, mechanical movement here, and this mechanical movement is captured and is converted to the angular movement of the indicator. So, there is a mechanism here which converts this angular movement, because when the tube is pressurized, it will try to again move in a circular direction like this, right. So, this movement is captured with the help of a mechanism and it is reflected on an indicator diagram. There is an indicator, and these gauges are, I mean, it's quite cheap and readily available in the market in different ranges. So, these pressure gauges, dial type of pressure gauges are very popular. Another is, nowadays pressure transducers are used. Now, the pressure transducers are electronic devices. They are electronic devices, right? And there is a, let us, okay, there is a it's an active type of transducer. Active type transducer means it requires external energy to activate, right? And it has a diaphragm. Diaphragm, either a strain gauge or a piezoelectric crystal is fixed on the diaphragm. So, when there is a change in the pressure, there will be change in the strain in the diagram, or there will be strain on the diaphragm, or if there is a piezoelectric crystal, there will be certain EMF output, because when the piezoelectric material, when it is compressed, EMF is generated, right. So, these signals are converted into the output, and in most of the transducer, any transducer you take, they have certain range of the output. I mean, either it is 0 to, this is very popular, 0 to 10 volt DC. Sometimes it is plus minus 5 volt DC also, depending upon the manufacturers. Either you can get output in voltages, or output is also given in amperes also, 4 to 20 milliamperes. This is also is very standard output of the transducers. This type of ampere output is normally taken when the distance between the location of the transducers and the data acquisition system is quite far, right. So, there will be no loss in the current, but if you take this type of transducer, when the distance is too far, then the voltage drop will take place. In that case, in situ calibration of the transducer has to be done. In fact, there are diaphragm type of transducers also, right. On a diaphragm, there is a strain gauge, the principle is same, and this strain is captured. In electronic type of transducer, there is a ready-made housing where all the arrangements are made. Otherwise, the output of this strain gauge can directly taken on a data acquisition system, and accordingly it can be calibrated first with the help of a pressure gauge, and then it can be used in the plant. Now, material for this type of system is, we can go for nickel, chromium or Fe, ferrous. Elastic limit is limited, it is 560 megapascal. Beyond this type of diaphragm type of gauge, strain gauge does not work. But diaphragm of strain gauge has certain issues also. First of all, it has hysteresis issue. Hysteresis is that the output of the instrument depends upon the direction of loading. Suppose direction of loading is 0 to 10, right, and input is increasing. So, output of the instrument will also increase, and you will get a certain reading, let us say 6.5. Now, you keep on increasing the input, or right, when you reduce input to the instrument, you may get, for the same input, you may get reading around 6.7, right. So, this indication or the reading taken by the display by the instrument will depend upon the direction of the loading. This is known as hysteresis. and in an ideal instrument, the hysteresis has to be 0. Second thing, if you take any transducer or this diaphragm type of pressure gauge, amplifier is required, amplification is required. That is why we need always external energy system to activate the transducers of this type of gauges. That is why they are known as active type of devices. And these gauges are susceptible to the shocks and vibrations also. So, a lot of care has to be taken that there are no shock or vibrations at the location where these gauges are fixed. In comparison to that, if you look at the manometer, again, manometers are cheap, they are not very costly, their accuracy is good, right? Maintenance is not required. I mean, they are relatively cheaper and more reliable. But there are other issues with the manometers, they cannot take dynamic load, and if you take the YouTube manometer, it is made of glass, so it is fragile also. Manometers are suitable for the low pressure. For the low pressure readings, they are quite suitable. But recording cannot be done. In the recording is the main issue nowadays, the recording. If you cannot record the data, then I mean the applications become limited. So, that is why this is the main reason for having limited applications of manometers. Sometimes you use two fluids, they are not compatible with each other. They get mixed up or they react with each other. So, care has to be taken. You take two different type of fluids, they are not miscible with each other if you are using multi-fluid manometer. Sometimes while taking the reading, meniscus is also a problem, meniscus height is also a problem, right, and viscosity is also there or capillary effect is also there. So, that all these things are still keeping in all these restrictions in a view, manometer, if you want to have accurate measurement of the pressure, still manometer is the main device. But nowadays we are going for the electronic type of system. So, electronic type of pressure measurement, mainly these devices are dependent on change in resistance, right, change in capacitance mainly, or some induction effect. Right. Now, we'll consider this in the case of this happens in the case of pressure measurement, and if you go for the temperature, let us talk about the temperature measurement. If you go for the temperature measurement, these principles are used, right. The main device or not device, main sensor which is used for temperature measurement throughout the world is thermocouple, for several reasons, right. And thermocouple works on the Seebeck effect. Now, Seebeck effect says there is a junction of two dissimilar materials, right. If one junction is hot, another is cold, and they are connected, then EMF will be generated. Now, this EMF is proportional to the temperature difference, not directly proportional, it is only proportional, right. And if we take cold junction, if you fix the cold junction, then variation in hot junction will be reflected in variation in EMF. The cold junction is normally fixed as melting ice, means ice plus water, and this is pure water or triple distilled water or demineralized water, right. So, the temperature of this is 0 degree centigrade. Now, this temperature is fixed. Now, hot junction temperature is measured and it is directly related with the EMF of. So, their charts are available, thermocouple charts. Nowadays, instruments are coming, their inbuilt calibration is there. They just simply take the EMF and they give display of the hot junction temperature, right. First of all, why they are popular? They are popular because first of all they are rugged and they are inexpensive. Completely we cannot say they are inexpensive because the cost of the thermocouple varies from 5 rupees 5 per meter to maybe rupees 2 lakh per meter, depending upon the type of the thermocouple and the type of application. but their response is very good. They are fast in response, and the response of the thermocouple depends upon the tip diameter of the thermocouple. Um, we can have thermocouple or wire up to a diameter of 0.25 mm as well. It is quite thin, 250 microns. This can be the diameter of the thermocouple sheath. So, because normally there are different type of thermocouples, there is a thermocouple wire, then wire often is covered with a sleeve. That is not a very costly type of thermocouple, so that this part of the wire does not come into the contact with the fluid. There is a sheathing also. There is a sheath on the thermocouple, so there is a thermocouple. It is covered in a tube, and rest part or this void space is filled with the. It is minerally insulated. Normally, it is MnO2, 99.9% MnO2, and this thermocouple is put in the sheath, and tip of the thermocouple is in contact with the sheath. Right? It can be stainless steel or Inconel. Now, sometimes what happens, suppose there is a surface where charge is flowing, surface is charged. So, charge will enter the thermocouple, right? Charge may enter the system also. So, there are two types of thermocouples, grounded and ungrounded. So, this is when it is in contact with this is grounded thermocouple. If I want to make it ungrounded, inside the sheath, the tip of the thermocouple will no longer remain in the contact. It will be very close to the sheath, but it will not remain in contact with the sheath. So, isolation of thermocouple tip takes place from the sheath. So, this makes the ungrounded thermocouples. Thermocouples are classified T-type thermocouples. They are very popular. Copper constant and thermo. Constant is a copper nickel alloy, right? Then T-type thermocouples, J-type of thermocouples. This is iron constant type of thermocouples. Then there chromel alumel is used for the K-type of thermocouples, N-type of thermocouples, T-type of thermocouples. Some are upper crust class thermocouples. They are B-type thermocouple, S-type thermocouple, R-type thermocouple. They have these thermocouple wires. There are two dissimilar wires, but they are made of different material. So, depending upon the cost of the material, the cost of the thermocouple varies, right. For example, this K-type of thermocouple, this chromel alumel alloy is used for this type of thermocouple, and they have a temperature range also. This T-type thermocouples can be used from minus 270 to 370 degrees centigrade. Up to 400 degrees centigrade even we can use this T-type of thermocouple. J-type of thermocouple can be used, let us say minus 210 to around 760 degrees centigrade. The J-type of thermocouple can be used. K-type thermocouple can go up to 1200 degrees centigrade, right. N-type of thermocouple can also go up to 1200 degrees centigrade. Now, rare earth, this R-type of thermocouple, it can go from minus 50 to 1500 degrees centigrade, right. Likewise, there is a range for different type of thermocouples. In addition to the thermocouples, there are other devices which are used, which is resistance temperature transducers, RTD devices. It works on the principle, if the resistance of the material varies with temperature. If you increase the temperature, the resistance will change. So, R is equal to RO 1 plus alpha delta T. It works on this principle. So, a thin wafer of tungsten is sandwiched between two plates, and current is passed, and with the change in the temperature of this metal or this tungsten, the resistance of with change in the resistance, the temperature is determined. So, this is a very good device. It can go up to 1000 degrees centigrade. It can measure up to 1000 degrees centigrade, and it can measure very accurate temperature up to 0.1 degree centigrade as well. So, if there is a change in temperature has to be measured, then RTD is the best device. After that, there is a device which is known as thermistor. Now, property of the thermistor is that it has negative temperature coefficient. So, if you increase the temperature, the resistance will go down. When the resistance will go down, more current will pass, the temperature will increase. The situation will come, the thermistor will come in the equilibrium with the surroundings, right? And its response is very non-linear type of response, but the response is very good and it can be used for -100 to 300 degree centigrade temperature measurement. And there are many other devices which can be used for the temperature measurement, but mainly these type of devices are used. These type of sensors are used in the power plants for temperature measurement. Now, for the flow measurement, first is Venturi meter. So, Venturi meter has a converging and diverging passage and it works on the Bernoulli's principle, as all of you must have studied. So, here this is section 1, this is section 2, and here a U-tube manometer is used in Venturi type of flow meter, and because either here the velocity has increased. I will not write the equation here because you must, I suppose that you have already studied this type of devices in fluid mechanics course. So, when the fluid, the velocity is changed, when it is a converging section, velocity is reduced, sorry, velocity is increased at the expense of the pressure. So, so the pressure here is low and pressure here is high. So, this pressure difference H, this pressure difference or pressure difference equivalent to this delta H has been converted into the velocity or velocity change in the velocity. So, delta P upon rho is equal to V2 square minus V1 square by 2, right. So, if V2 is very high than V1 or V2 V1 are comparable, in that case also we can find the velocity of the fluid which is flowing in a pipe. So, this is because V1 V2 can always be related, A1 V1 is equal to A2 V2. So, V2 can also be taken as a function of V1, oh sorry, V1 can also be taken as a function of V2, vice versa. So, that is how we can get the velocity of fluid. Another most powerful and more widely used is rotameter. Rotameter has a diverging passage and a float, right. And this float, when the velocity of the fluid is increased, accordingly, this float takes position at different heights in the vertical. It is always vertical. Rotameter is never horizontal. That is the, one of the limitations of the rotameter. It can be installed in a vertical direction only. Venturi meter can be installed in horizontal and vertical. There is no issue. But the issue with the rotameter, it can be installed in a vertical direction, and the flow will decide where the bob will get balanced. And the pressure balanced is drag force plus. This is density of the fluid. Normally, it is water, density of the fluid, and G is equal to. So, it works on the, it is Archimedes principle also. So, Fd is equal to rho b minus rho f Vb into G. Now, drag force is drag coefficient rho f um square divided by 2. From here, we can calculate the value of Fd, and when we are putting this value of Fd here, we can always find the velocity, mean velocity of the fluid. There are other flow meters, there are number of flow meters. One is magnetic flow meter, which works on the electromagnetic induction, and there is a flow meter which is known as turbine flow meter. In turbine flow meter, a small turbine is housed in a pipe, and when the water flows through the turbine, turbine starts rotating. So, RPM of the turbine, the flow rate, volumetric flow rate can be a function of RPM of the turbine, right. So, turbine flow rate is there, vortex flow rate is there, vortex flow rate is there. If bluff body, now if a bluff, there is a bluff body, like a cricket bat is a bluff body. So when the fluid flows over the bluff body, eddies, vortices are formed behind the bluff body. If you are able to capture the frequency of these vortices, it is SV over L, right? Uh, L is the characteristic length, V is the velocity, S is the Strouhal-Hall number, and F is the frequency. If you use this correlation, you can, these appears to be, I mean, it appears that this flow meter will not be very accurate, but practically it has been found for the, especially for the low flow rate, these flow meters are very effective, right? One of another flow meter which is very popular in the industry is Coriolis flow meter. Mass flow meter, because here most of the flow meters, they are volumetric discharge flow meter, and then volumetric discharge is multiplied by the density, and that is how we get the mass flow rate. But in Coriolis flow meter, we directly get the mass flow rate, and in Coriolis flow meter there is a tube, and fluid flows in a tube, and tube itself vibrate. So due to Coriolis effect, the tube gets bent. Suppose there is a tube here, this is a tube, right? And when the flow is taking place inside the tube and the tube is vibrating, then both the arms of the tube will twist, and angle will be twist at an angle, and this theta angle. So mass flow rate is always a function of this angle theta. So by putting a proximity sensor here, we can always find the value of theta. Once the value of theta is known, we can always find the mass flow rate. So these flow meters are quite popular in the industry and they are quite accurate, right? So these are a few examples I have given you for the instrumentation in power plants. Otherwise, there are exhaust gas analyzer, there are spectrometers, there are n number of instruments which are used. They cannot be covered in one lecture. So there are n number of instruments which are used in a power plant, but mainly in a power plant, flow of the measurement of temperature, pressure, and fluid flow is quite critical, right? That is all for today. Thank you very much.